Good evening. Let's wait for 3 more minutes and then we'll start. Okay, we can start our class. Is my PPT visible? So, welcome to the
Yes,
week
madam.
8. Okay, Fundamentals of Additive Manufacturing. If you have any question from the week 8 videos or lectures, you can ask me. Do you have any question?
No, madam.
Okay, so did you watch the videos? Did you watch the videos?
Yes, madam.
Okay, okay, then if you don't have any question, then we can have can you mute yourself? Are having such some background noise. Okay, thank you. So if you don't have any question, we can start getting a recap of the topics that have been covered in the lecture 1, 2, 3 of week 8. And in between, if you feel any question, just stop me and ask me. So in week 7, we got to know about the FDM process and how the wire get deposited over the well plate, how the layering happens, how the beads start forming, and how the bead gets the overlap bead, and how they form the uniform flat bead. What should be their condition, optimal process parameter, all the stuff we have read about. And then in week 8 lectures, excuse me, we have watched how the other wire additive manufacturing take place. So now we are going to know about another wire AM process, which is known as WAM, where arc additive manufacturing. Now this WAM comes under which state of the art? Do you know? Additive manufacturing has 7 state of the art according to ASTM standard. In which state of the art this WAM comes? Do you know? Any idea? Okay. So we have the directed energy deposition process, which comes at the end of those seven state of the art, because this directed energy deposition or DED process utilizes the maximum amount of heat source. Because in the ASTM standard, the order of the state of the arts were in such a way that the first VAT photopolymerization uses the least amount of heat source, and DED uses the most amount of heat source. So in under DED, this WAM comes. So in DED, I'll go like in another way. So the material aspect, if I take, in DED we can use powder, we can use wire, and in energy source aspect we can go to laser, we can go to arc, we can go to electron beam, we can go to plasma. So these all are different energy source that are utilized under DD. So DD is the process which uses the maximum combination of heat source and material source. But DD is not suitable for polymer. DD doesn't use polymer because already I have said DD uses the maximum energy heat source among all other state of the art. So polymer needs very lesser amount of heat to get melted or sintered. So DD doesn't use polymer. DD is not capable of printing polymer parts, but any type of metal can be printed using DD. Now, the other metal additive manufacturing is PBF, powder bed fusion, and DED is the last one. So, among powder bed fusion and DED, there are a lot of controversy and there are a lot of differences and similarities, because these two processes are the mostly used process in additive manufacturing to print metals. But people uses PBA for different application and uses DAD for different application. But you will see NASA is using DD and LPBA both to print their parts for different applications. So they are using WAM, they are using wire laser, they are using powder laser, and they are using laser powder bed fusion. So now we were talking about WAM process. So if I talk about WAM process, then there we use wire as a material and arc as a heat source. Now this combination of arc and wire from this DD3 gives rise to WAM. As you have already seen the videos and you have already understood those video lectures, so there is no such point of describing the videos again. So maybe I will pick up the most important points from those three lecture videos to summarize here in this doubt clearing session. At the last, we will be discussing about the week 8 quiz questions from last year, and I will also add some more point to this three lecture series, lecture videos of week 8, so that you can get an overall concept of WAM in terms of metal additive manufacturing. So, other than these three, we have powder and electron beam. We have powder laser, which is called normal DD or powder DD. This is also powder DD or electron beam DD. This is also called laser DD. Now, where wire laser is also wired DD. Plasma and wire is also there, which is not WAM, but something comes under DD. And these are few combinations. So, when we are using wire, obviously the heat source to be utilized will be the most rather than for powder, because always remember one or not one but few important points. When we supply powder to the deposition process using any nozzle, there will be air gap, and along with the powder we supply the laser as well. This is the DD, okay, through the nozzle. So there will be air gap, and when they are getting deposited over the build plate, the part will utilize less power than when you will be using wire and you will be using laser. So this can be like, this is the wire, this is laser, okay, and this is powder. But if you are using wire will be much thicker. To melt the wire, you have to provide multiple laser. So you may provide two, three, four, six number of lasers to melt the wire, and the bead will be deposited then. So here the heat source or the amount of heat needed is more than powder one. So that's why DD utilizes the maximum amount of energy than any other state of the art of additive manufacturing. Now, what happens in WAM? So, if you have any doubt, just ask me in between. Stop me and ask me. So, in WAM, what happens is, so the wire will come and the arc is coming. Okay. So, uh, to make the arc, we have to have a electric connection. So there will be a cathode, there will be an anode, something will be plus, something will be minus, any of these two things, so that there can be an arc established between the electrode and the between the cathode and the anode, and then we'll get an arc. So here what happens, we make this this thing. Okay. So next, what happens when we establish an arc in the substrate, or how should I? This is my substrate. Okay. Now, if I make the substrate positive, and this is the electrode, if I make this electrode negative, then this electrode is consumable. So now we get the essence of MIG welding. So this WAM process is basically got inspired by the various welding techniques by which we deposit material over the joint to weld two substrate. So that process is repeated multiple times to get a layer by layer effect of the same welding, and we can build a part, a 3D component. So if this is so, then there will be heat. The substrate will be more heated. Substrate will get the most amount of heat, and it will have a very high penetration of the arc, or the effect of arc will be till much depth, and over which the bead will be deposited by melting this electrode. So this part of the electrode is melted, and now it is deposited over the weld plate. But in WAM process, we want the electrode to be deposited over the build plate. But if we are getting very high penetration inside the substrate with each layer, what will happen? In welding, we need a very high penetration inside the substrate. There, nothing is called as substrate. That is a welding process. So anything you want to, so there is no substrate. There is two metal that you want to join. Now, if you want to join two metal and you are using a consumable electrode, the electrode will get melted to add some extra material over the joint, and you want the joint to take place throughout the two metal part. So you need a through penetration to both the metal plates that you are using to join. So there you need a very high penetration. Also, in case of laser, there will be a focus point, and laser welding takes place in focus point. Laser will look like this. This is the Rayleigh range. This is called Rayleigh range. I forgot the spelling. Maybe it's like, I don't know. So this is the Rayleigh range in which you get the 5% focus. So this is basically the focus, and you weld the substrate like in focus. But in case of DD, if we are melting the material, we never do it in focus. The laser will be like this, and here the deposition takes place. Because we don't need very high penetration depth inside the substrate. Why? We want the material to be deposited over the substrate, and we want the fusion between the first layer of with the substrate. This is true. But now you imagine when you will be printing multiple layers. So when you are printing first layer, your first layer, the bead is your bead, substrate is substrate. But when you are printing second layer, your bead is your second layer, but your substrate is your first layer. When you are printing third layer, your bead is the third layer, but your substrate is the second layer. है ना? So if you are continuing this process with multiple layers, and if you are getting very high penetration depth for each layer deposition, it may happen that at the time of fourth layer printing, your bead is fourth layer, but as your penetration depth is very high, your penetration is going up to first layer. And even it is melting the substrate as well. So if you are giving this much heat input, which is not necessary there, it will just be wasted, and it will just increase the residual stress inside the part, because that heat will not get sufficient space to get dissipated inside the part and in between the process. So that will just increase the residual stress inside the part. And when your printing will be done, now if you will be trying to cut the part from the build plate, your part will be cracked. You will have cracking throughout the part. Your part will be bent. Your part will be distorted. So why to then waste your part just by wasting energy? So this is why we can save energy and make the process more efficient. So both the way we are optimizing the cost. So why not to go for that? So that's why we don't do the this welding condition where you make the electrode negative in case of arc MIG process. Okay, MIG WAM process. You will not do that. will see that you will be using this electrode negative in another type of welding, in another type of one, but not in big MIG WAM. Because in welding, you are not very much concerned about the consumable electrode. You are concerned about the build plate, but here you are concerned about the consumable electrode, because that is the raw material for you. So that's why we use the electrode positive configuration. This is the arc coming. Along with it will get melted and deposited over the build plate like this. And this is the build plate negative. Here you will get a very shallow penetration depth inside. In DC, it's fine, you can go with it. But if you are using AC, then again, each time you are reversing the polarity. So because of which, again, you get more penetration inside the substrate than DC, but you can work with this as well. And in some cases, if you are constantly printing something in WAM in electropositive mode, this DC electropositive mode, then aluminum like materials get oxidized very easily. So you will get oxidized layer on each layer, on top of each layer deposited. So that's why AC is much required in case of aluminium. Because in case of DD also, when you are using aluminium, you have to have a very controlled argon gas. Matlab, if you are not providing sufficient argon gas, everything will be oxidized there. So aluminium is a very tricky material to work with in additive manufacturing. That's why people do not generally use aluminium. But I know it's very difficult to work with, because I am having my PhD topic. My PhD is on aluminium. So in case of WAM, you have to provide AC current, so that whenever one track is deposited, now you will have oxide layer. Now when the polarity is reversed, the oxide layer will be broken, because there will be sudden increase in the current, and that current will just break down the oxide layer. So there will be no interrupt in between the oxide layer formation, and in the repetitive cycle you'll not get oxide layer on each deposited AL track. So like that, in some material you need AC. You can go with AC, but DC can also work with electropositive mode. Now, if I talk about other, okay, one thing is like in case of FDM, we saw that there will be a spool. In that spool, your wire will be stored here. Wire spool, we call it. And from that wire spool, it was coming through the, yes, I know the name, pinch roller. And from the pinch roller, it was coming to the nozzle. This was the FDM process. WAM is nothing but same, okay? So there will be a spool. From the spool, the wire will come. Here also, pinch roller type mechanisms are used to pass the wire, to make the wire in tension. So there will be a tension in the wire, so that the wire shouldn't get bent, or there shouldn't be any deformation in the wire. Also, to maintain the feed rate, also this type of pinch roller mechanism is used in WAM processes as well. So it's almost like same, but here there are some electrical connections with it, so that we can make the wire an electrode, and then it will come to the build plate. Here inside it there will be the electric connections. This is WAM. It's almost same. So when you are using this, where is this slide? Okay. So we also called this thing as reverse polarity. So people use direct polarity, people use reverse polarity, and AC polarity as well. So now, if I talk about the process parameter of WAM, so as you have watched the videos, so can you name the process parameters for me so that we can discuss about the process parameters and how we can affect the build quality by optimizing the process parameter? Anyone? I have already described the process. You can just unmute yourself and tell me. And Pranav has raised his hand, so if you have any doubt, you can ask me. Any doubt, Pranav?
What is the full form of WAAM, ma'am?
Okay. Yeah, I was describing that. So it's so have you watched the videos of week 8?
Yes, ma'am.
Okay. So WAM comes under the DED, Directed Energy Deposition type of additive manufacturing, and WAM stands for WAAM stands for wire arc additive manufacturing. So can you tell me the process parameters in used in WAM? Kiran, Pranav, anyone? Just guess or try something.
Say one of the parameters is wire feed.
Wire feet. Other things. So let's go one by one. Okay. So now let's talk about wire feed. So in case of MIG welding, using consumable electrode. So now wire feed rate is like as definition at how much speed the wire is coming from the spool. Now this speed is also dependent upon the traverse speed or deposition rate also. So there is one thing called wire feed rate, another thing called deposition rate. So these two things are not really similar, but to some extent similar. So we can also take another name called traverse or travel speed, something like that, or traverse rate or speed. So one is like the wire is coming out of this head. This is the deposition head. Now, as we are talking about additive manufacturing, so obviously this deposition head will move in this direction at the time of printing. This is my substrate. If my substrate is not moving, it is stationary, then my printing head will move. If my substrate will be moving, then my printing head will be constant. So let's take an example of printing head is moving. Now the printing head will move, and along with that, the wire is coming continuously from the spool. So that speed is called wire feed rate, and the speed at which the wire is traversing or traveling over the substrate. That is the traverse speed or deposition rate.
Ma'am, screen
Yes.
is not visible, ma'am.
Oh, screen is not visible. Is it visible to Pranav?
Yes, ma'am.
Okay. Is it visible? Who said it's not visible? Kiran or Pranav? Is it visible now?
Yes,
Yes,
ma'am.
madam.
Now it's okay, ma'am.
Okay. 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 So if my substrate is stationary and I am moving my printing head, then the rate at which my printing head is moving, that is the deposition rate. Now, if your deposition rate, now try to answer this question, okay? Deposition rate is very high. What will be my wire feed rate? Just answer like it will be high, or it will be less, or it doesn't matter, or it doesn't depend on that, or it will be constant. If my deposition rate is high, what should be the probable answer?
Feed rate also needs to be high.
It should be high. Okay. So the wire feed rate should be high. Why? So my deposition rate is high means the head is moving very high, fast over the substrate. Now, if my head is moving very fast, the bead should be properly deposited over the substrate. So for the bead to be deposited over the first substrate, the wire is depositing the bead. So the wire is getting melted and deposited over the substrate. So the wire should come fast to match the deposition rate, to match the speed of the travel head or deposition head. So that's why the wire feed rate should be high, and thus the wire feed rate is dependent upon the deposited head and vice versa. Now, again, one thing is like there is no limit of high and low. There should be an optimal limit, an optimal speed. Because if my deposition rate is high, then it's good. We will get the whole printed part in a very small time. But again, the spool is rotating and the wire is coming. So it should not be the case that the deposition rate is so high, like the deposition head is moving in a particular direction so rapidly that the wire could not match the speed, although the wire feed rate is at the highest value. But still it cannot match the deposition rate, and now you are not getting optimal bead. So the bead which is getting deposited over the bill plate like this bead should be the structure something like this what I have drawn. The upper surface should be as much flat as possible, and now you will have the overlap. Now from the last lecture, if you can recall, then in FTM there was a process. There was those things like 2 by 3 these things. Sorry, yeah, something like this, 2 by 3 bead width. If you are maintaining the optimal condition, then only you can get the flat surface after depositing multiple layers with a particular overlap. So that's why it's very important to get an optimal deposition rate rather than the highest deposition rate. Now, can you name also another thing? If your deposition rate, like the head movement, is slow and your wire feed rate is medium, what can be happening in that case? in the deposition. The wire
Lag will
feed rate. Sorry, can
lag
you
will
repeat?
lag will be seen.
Uh, what I
There
couldn't understand.
there will be continuation of the material laying on the build platform. There will be a lag.
Yes, there will be a lag. Okay, so
Yes, ma'am.
the lag means it will happen when the deposition rate. What I mean me understand by lag is the deposition rate is high, but the wire feed rate is medium. Then the wire feed rate is not enough to come and form the bead. Then there is a lag. But when the deposition rate is low, but wire feed rate is medium, then what will happen? You try to imagine and answer me. No. So if my deposition head is moving very slow and my wire is coming in at a medium range, so this is fast, this is medium, this is slow. So medium is obviously faster than slow. That means there will be more material coming on the substrate than what is needed. So required से ज्यादा आएगा material. So if the wire is coming more than what is required, then there will be slack formation, there will be sputter, there will be undulation over the build plate, and other things like if the more material is coming, so this may be like this, the bead. The bead may look like this because more material is coming than what is required. And also there will be slack formation, sputtering, and due to sputtering there will be defects like porosity and all those things. Okay, so this may be one situation if the deposition rate is slower, but more amount of wire is coming and getting melted over it. And if more amount of wire is coming na, so if the wire is dropping by, drop by drop, so there is a melt pool over which you are depositing. Now more number of drop is coming, so there will be, when the drop is coming, when the melted metal is dropping inside the melt pool, there will be sputter. Now, if no more number of drops are coming than what is required, more number of sputtering, there will be very much instability in the melt pool. Due to the instability in the melt pool and more heat input is coming. So if wire is coming more means heat input is also coming more because wire is containing the heat. And along with the arc. So obviously, if more arc is also coming, more heat input is coming, residual stress will increase, and due to the more heat sputter generation, due to which you'll have keyhole effect, you'll have porosity, will you will have very much what I have said, instability. So these may be a one probable cause if your deposition rate is low but wire feed rate is okay, medium. So the next question is, what is the second process parameter? First, we have discussed which is the wire feed rate. And along with wire feed rate, I have also discussed about the deposition rate, which was the other process parameter. What can be the next process parameter in WAM, according to you? No need to memorize the lecture or no need to remember what was said in the class. You just try to answer by your own. Suppose I also don't know what is the process. By seeing the process, by looking at the process, what has been discussed here, try to tell me what can be the other process parameter. Material temperature.
Using nozzle, ma'am.
Sorry, can you repeat?
Using nozzle, ma'am.
Using nozzle, what? I am asking about the process parameter. So you said material temperature. I am not very much going with your point because what do you mean by material temperature? No. Can you explain what do you mean by material temperature? Let's be interactive in this session because the motive behind this session is interaction, not lecturing about something, because the lecture has already been given by professor. What I understand from the process is, the electrode is coming, the electrode is getting melted and depositing the bead over the substrate. This is first situation, this is second situation. And this is how the process take place. And how the material gets melted, because material is actually an electrode which is positive, and the arc is getting established between the electrode and the build plate. So because of that arc, the material is getting melted, the electrode is getting melted. So there is nothing called material temperature, because what will be the material temperature? You are providing one voltage in between these tracks, and because of which there is the current passing through, and the arc is getting established through the build plate. And due to that arc, the electrode is getting melted. The electrode is melting itself. So can I tell that the current which is passing through the electrode is one process parameter than the material temperature? Will you agree with me?
Yes, ma'am.
Okay. So now we have another question, that how the current will affect. So just remember, when the current increases, the temperature increases. If the temperature is increasing, again I'm coming to this point, material temperature. So if the material temperature is increasing, so the melting will be much easier. So if the melting will be much easier, then the deposition will be much easier. because deposition means I have to melt the electron and deposit it over the build plate. Now what is deposition में ऐसा क्या है? I have to just melt the material, and if it is getting melted due to the gravity, it will fall down over the build plate, right? So my current is an influential parameter here. So if I increase the current, I'll have deposition in an easy way. And if I decrease the current, melting the wire, melting the electrode will be difficult. Now, there should be an optimal amount of current again. If you increase the current very high, then the temperature will be so risen up that you will have instability in the melt pool again. So you have to have an optimal condition of the current. So this is my second process parameter. So what can be my third process parameter? So if current is my process parameter, I would say voltage is also my process parameter. So current and voltage are bhai behan. So if we are increasing the current, we'll increase the voltage, something like that. Okay. So हमारा equation चलेगा तो V equal to IR से ही ना. So if you are increasing the voltage, decreasing the voltage, you can just control the process. So what can be my other process parameter? Now think about something else, because I have already mentioned, I have already discussed two, three. Any other thing?
Gas flow rate, ma'am.
Gas flow rate. Now can you tell me where this gas flow rate or gas is used in the welding process? What is the utility of gas? उसके बाद आता है gas flow rate as a process parameter.
Ma'am, no idea, ma'am.
Okay. So in case of additive manufacturing, when you are depositing the material over the build plate, you are creating a melt pool, and now you are traveling with the melt pool. So if you are creating a melt pool over this build plate using an arc, it is okay. It is a good process that you have established. Now you are moving this arc. So this is at time equal to 0. This arc is time equal to t, and this is the arc at time equal to tn. Okay, and the melt pool is also moving, and now the melt pool has come here, and this is the deposited track, because the arc has moved from t equal to 0 to t equal to n, and now this is the arc which is getting, this is the deposition bead which is getting formed. So if your arc is moving, your melt pool is moving, so and also you are depositing something in the open air environment, then at that high temperature of the melt pool, you may entrap some gases from the environment. You also can entrap other material, other ions, other something which is not required in the melt pool zone. So in any additive manufacturing technique, not any, but metal additive manufacturing techniques, because metal uses very high power, very high energy density of the heat source, we uses a gas which will be present like this. This is a gas which will cover the melt pool, which will cover the deposition process. It will have a certain flow rate, it will have a certain pressure, by which you can make the process contamination free. You can make the process environment constant. To maintain a constant process environment and to maintain the contamination free deposition, we provide a particular gas. Now, gas means there are a lot of gases what you can use. So also there is a specification of the gas. So we basically use nitrogen or argon as a gas, because these two gases are cheap, first of all. Next, they are heavier than air. If you are using normal air, compressed air, it will not stay there. But if you are using high pressure nitrogen or high pressure argon, then they will stay in that deposition process, because they are heavier than air, and also they do not react. If you are using something reactive, then your gas will itself react with the melt pool and you will get some defect in your deposited feed. But these gases, argon, nitrogen, are reaction free, so they do not react, even they do not react at high temperature. Because in the melt pool or near the melt pool, the temperature is very high. It's something around 2000 or 3000 degrees centigrade. At that high temperature also, these gases do not react. So this is why we use argon or nitrogen gas in the deposition process as a shielding gas. So we call it as shielding gas. We also call it as shrouding gas. Now you are reading about VAM. You will know, you will heard the term gas flow rate. But when you will start learning about DED, which is the actual actual uh, like additive manufacturing technique, not like welding, there you will get to know this shielding gas, shrouding gas. Okay. So these all are same gas, just their purpose is different. One gas will be used. So the purpose is also very important. One purpose is to maintain contamination free constant environment, protect the melt pool from contaminant or other ion and material or gas entrapment. Also, to provide to provide a constant shape of the melt pool. Okay, so the gas flow rate will be high, so that the shape of the arc, so the arc is coming like this, and the melt pool is the deposition is taking place like this. So the gas flow rate will be in such a way that if this is the arc and this is the gas, the arc will maintain its shape like this, and the melt pool will also maintain its shape like this, because originally when the arc comes from the up, the arc will have a Gaussian profile. Okay, so this Gaussian profile should be maintained. So the gas flow rate ensure this constant shape of the deposition process or melt pool. Arc or deposition. So you can note down those points. These are important to know about aim. So gas flow rate. Now let's come to gas flow rate, which is the process parameter. Gas flow rate is a process parameter. Yes, it is, because we have to provide a very high gas flow rate so that we can maintain that shape of the arc, to maintain the shielding process, contamination free deposition. But again, do you feel that the gas flow rate will be very, very high or just high? What will be your answer? And if not, then why? So my question is, can we increase the gas flow rate according to our choice, or will it have any effect on the melt pool?
Yes, ma'am. Then only the melting will happen fastly, no, ma'am.
Melting will happen faster, you mean? Why? Because of the gas flow rate, the melting will happen faster. What do you feel? Whatever you understand, whatever you feel, you can discuss.
In the case of increasing the temperature, ma'am.
But we are talking about the gas flow rate, not the temperature. What will happen if I increase the gas flow rate? Let me reframe my question. So, what will happen if I increase the gas flow rate? No?
Ma'am, you itself tell, ma'am.
Yes, yes. So, um, if I increase the gas flow rate, we will to some extent just protect the environment and maintain the shape of the deposition process or shape of the arc. We can minimize the spatter as well. We can minimize the spark in the unnatural spark in the arc. But if I increase the gas flow rate very high, then you imagine the gas is coming directly onto the melt pool. Maybe there is a distance between the gas coming and the melt pool forming, but still gas is means the argon nitrogen, so these are like air. So if some gas is coming with a very high velocity, it can just, this is the melt pool, this is the melt pool, and this gas is coming like this. So it may happen the gas is with high pressure is coming, so it will just penetrate inside the melt pool with that high pressure, because the gas flow rate is very high gas flow rate we are talking about. So if gas flow rate is high means the pressure is very high. So with that high pressure, if by chance it is penetrating inside the melt pool, then what happens? It will just form some gas bubbles inside the deposited track, because when it is going inside the melt pool is having the thicker metal. It's the argon is heavier than air, but it cannot be heavier than a metal. So if it is by chance going inside the melt pool, now it cannot come out. This process will not take place. It cannot come out because now heavier melt pool is there, heavier metal is there, and as it cannot come out, but again drop by drop, the this upper surface will not be flat, it will be like this in the melt pool, because drop by drop the electrode is getting melted and deposited in the melt pool. So there is instability already in the melt pool, and now the gas is also coming. So high flow rate will increase the instability in the melt pool. It will get entrapped inside the melt pool and will form the defects like gas bubbles, gas entrapment. So actually, these give rise to porosity in the deposited track. So this is why you should not have the gas flow rate higher than the optimal. So what I, the every time I'm talking like this should be, and this should be used with an optimal value, because if I am talking about one parameter and if I'm mentioning that this should not be very high, this should not be very low, this should be with optimal value, means it is a parameter which is influencing the deposition process. Then only I will talk about that now. So that's why every process parameter should have an optimal value. They should not be used with a very high or with a very low, like which is beyond the optimal range. It should not be used beyond the optimal range. So that is why it is called a process parameter, because this will have a influence over the process. Now if okay, now everything is gone. No problem. So we have talked about the gas flow rate. So first we have talked about current, then we have another which is wire feed rate, deposition rate, sorry, current and voltage we have talked about. Then we have talked about the gas flow rate. Is there anything else than these three process parameters that we have not talked about? that will be used as another process parameter. What do you feel about the stand of distance? So stand of distance is this is the electrode. Here electrode means our wire, and this is the substrate. So the distance between the electrode and the substrate is known as stand of distance. So in case of VAM, this is different than other metal AM process. In case of VAM, we are establishing one arc in between the electrode and the substrate. So the arc will be like this. If the arc is like this, then the stand of distance is very important. In other additive also, the stand of distance is important. But here I am giving much pressure on this word of stand of distance because in between this SOD, the arc is getting established. So if the stand of distance is very low, then when the drop is going inside the melt pool, it will spatter some melted material, and it can affect the electrode, it can affect the charge, it can affect the arc which is established there, or it can make some short circuiting in the electrode substrate, and it may just damage the whole process. If the standard distance is very high, like here the electrode, here the substrate, the stand of distance is very high, then the arc may not get established, first of all, because the circuit is not getting completed with the plus minus. And another thing is, even if the circuit is getting completed, it may happen that this height is so high that when the droplet is coming, multiple droplet is coming in one go, because stand of distance is very high, and when from a very top portion the droplet is dropping inside the melt pool, it will spatter a lot of melted metal here and there outside the deposition zone. It will create chaos to the deposition process. It will make the melt pool unstable. Sputtering will increase. If sputtering increases, then there will be gas entrapment again. There will be porosity in the process, and due to the instability, the surface roughness also increases. Like you will get undulation over the deposited track like this, rather than this will not take place. This will take place, and which is not required. This is required. So lot of problems. So stand of distance is also very important parameter here. Other than this, there can be other process parameters as well. For example, there can be the electrode, the composition of electrode, or the surface roughness of the electrode, like the diameter of the electrode, means the wire feed rate. We are having one process parameter, so why not to the wire diameter? So the wire diameter you can also vary, but generally you will get the standard wire diameter for a WAM process, so you don't have the uh, space to optimize this thing and make changes. But wire diameter you can also change as a process parameter, but people do not change, they use the constant thing because that is the established process. Again, other than wire diameter, you can play with the substrate also. For example, you can heat the substrate, then your material temperature will be one process parameter. You can heat up the substrate, so substrate preheating increases the deposition rate and increases the quality of the deposition. So substrate heating can be one thing. Next is that if the substrate is not flat properly, or the substrate is having some deformation over it, so the arc is getting established, because substrate is working as another electrode. So there can be hamper in that arc establishment. Also, the ambient temperature and ambient conditions may also affect the process, like ambient temperature, ambient humidity, etc. So these are not considered as a process parameter, but all these things have the influence over the process. But current, wire feed rate, deposition rate, gas flow rate, standoff distance, these are the mainly used process parameters. So this is what I have talked about on the MIG process, metal inert gas welding, or GMAW, gas metal inert gas welding, something like that. Then we have TIG process, tungsten inert gas welding. TIG, this was MIG. In TIG, we have studied about TIG MIG in our bachelor's. So in TIG, we do not use consumable electrode. So in TIG, it's non-consumable electrode. Okay. So if the now there comes the another interesting fact. If this is my substrate and my electrode is not consumable, that means my electrode is just making the arc. Now, if my electron is just making the arc, then from where my wire will come? So it should be side feeding. So this configuration is known as side feeding. In DD, side feeding is again very popular. In case of powder-based additive, powder-based DD also, laser powder DD or laser wire DD, you will find this side feeding configuration. This is also known as off-axis configuration. Off axis means if the heat source, if this is the heat source and the wire, so in case of MIG, the electrode which is making the heat source, it's itself the wire, so it is the coaxial configuration. The axis of the heat source and the axis of the melted wire is same, that is coaxial, but here the axis of the heat source and the axis of the melted wire is different. There is certain angle called theta, so that is why it is called off axis. It is off the axis, not on the axis. So in case of TIC process, you cannot have consumable electrode. So that is why we use here the other polarity which says the electrode negative. So in case of MIG, we uses the electrode positive we use in case of MIG. So in case of TIC, we uses this thing where you will have more energy, like 70% energy coming in the substrate. Tungsten material is used in the electrode, and here also this is for DC, and if you are using AC, then it is well and good. Again, as I said, aluminum is welded or used in additive manufacturing with AC type of WAM process. So next is in case of TIG, we are establishing the arc using the electrode which is made of tungsten. Now there is one concept called plasma. So if we are deionizing the material and then also you are providing the heat source, then that ions make the ion cloud, and which is known as the gases make the ion cloud. separated in ions, and that ion cloud is known as plasma. Plasma also have very high amount of heat contained in it. So plasma can also be used as a heat source. And in case of WAM, plasma is also used. So in case of TIG, instead of arc, you can also use plasma. So from here, the plasma will come, and from the side fitting, this wire will come. Don't think like rod in case of welding. In welding, we use rod, but in additive manufacturing, you will not just deposit one bead in between two metals. You will print a whole geometry over the build plate. So that is why you need a lot of wear. So it we do not use rod, we use wear, which will be mounted over a spool. And the wire from which it is coming, it will also come through the pinch roller, so that optimal tension will be maintained in the wire, so that the wire will not get damaged or buckled in between or bent in between. So these are few types of WAM process. There is another process which is called CMT. Do you know the full form of CMT? Excuse me. CMT का full form, अगर लेक्चर देखा है तो पता होगा. It is called metal transfer. Now, what happens in cold metal transfer? As name suggests, it is cold process. So one thing you imagine, you are depositing the metal onto the substrate, and metal has the melting temperature. It starts with 660, which is the melting temperature of aluminum. So cold means in room temperature or cool temperature, you cannot melt the material. Then why it is called cold temperature, cold metal transfer? Because you are not establishing any arc, or you are not establishing any plasma, you are not providing any laser or electron beam in this process. What you are doing is you are making the spark, you are making an arc which is instant, which will be there for few microsecond, and in that not microsecond, millisecond or second, and in that millisecond you will have a very high energy input for a given instant, and at that moment only your wire will get melted, and you'll get one drop of metal onto the melt pool, onto the substrate. So that's why there is no external heat source that is being provided inside the process, which you can see. You cannot see the arc or laser beam or electron beam which is coming in the process, but still there will be the heat source because it is coming under DED. DED provides the highest amount of heat source in than any other additive manufacturing process. We have to have the heat. So what happens is, here the funda is short circuiting. So it will make a short circuit. So it will touch the build plate, and when the short circuit is established, there will be very high current passing through it. So suddenly it will just retract. When it will retract, the current will be there will be sudden jump in current, and that sudden jump in current will produce so much energy, it will make a one drop of melt pool out of that electrode. And as you have, okay, it's gone. And as you have retracted it from the build plate, now there is no arc or current passing through the electrode or build plate. You have just deposited one drop. Now again, second step, it will come down, touch the build plate. As soon as it touches the build plate, now there is a connection of positive negative in it. So it will produce the short circuiting. Short circuit means no resistance, very high current. High current is very high means temperature increases. तुरंत ये ना आपको retract कर लेगा. It will retract back itself, and because of that high current you'll be having another drop of metal. So this is how it works. It works on the principle of short circuiting and retracting the wire from the melt pool. And as you are not establishing a constant current or not providing laser or metal or anything, so that's why uh, you call it as cold metal transfer, but it is not cold. Do I have any other? Okay. Another thing I forgot to mention, which is again very important. In process parameter, we have discussed about many process parameter. Some are left. So fifth process parameter I will write as the overlap. How can I forget this? Overlap ratio is very important in case of DED. In case of FDM, if you can remember, we were having one bead, and over the bead another bead was depositing like this, and there was this thing which was making it flat. Like if the bid width is something 2 by 3 bid width, you will have that surface roughness, something like that. You are having some equation. The same goes for here as well. Here also the overlap should be in an optimal range. So what happens, if this is one bead and this is other bead, and you have this, so it will be flat. If I have from one bead another bead, this will not be flat. So this will have that undulation, not flat. But if you are building like this, very high overlap ratio, then again overlap means you are providing high energy input, because along with the bead the energy is also coming. So on the previously deposited bead also, you are supplying very high energy, which is not required, it is already solidified. So because of that high energy then required, you will have unstability, and because of the instability you will have surface roughness, less density, more porosity, something like that. So defects, sputter, all those things. So overlap is one thing. Another thing is area filling. This is not a very basic process parameter. This is an advanced process parameter. If you are building this box, you can build it like this. You understand how my pen is moving and building this, filling this box. Now we are having this small gaps, right? Gap. Now because of these gaps, you will have porosity. So that's why overlap ratio is very important. If this is one track 1, and this is track 2, so bead overlap means when the nozzle is moving in this manner, it is depositing one bead another bead with the bead, which is the next layer or next track. It is the next layer. So one is the bead overlap, another is the track overlap, another is the layer height. So layer height is also a kind of overlap of one layer to the other layer, because when you will be printing second layer, the first layer will also get melted again. It will get some heat. So all this type of overlap is important. And area filling is how you are filling the area. If you are filling the area like this, you may have some porosity. So you may fill the area in this manner with a higher overlap ratio. As the overlap ratio is high, now there is no wide gaps in between tracks. You see? So here, no gap, no porosity, good. Now you can also feel the area, like first layer you are printing like this, second layer you are printing like this. So 90-degree rotation. So these are type of area filling techniques you'll use as an advanced process parameter to get an optimized density, highest density, least porosity, and optimized material properties. So this is all about the process parameter of WAM. Now WAM can be MIG, TIG, or CMT, plasma. Other WAM processes can also be there. As you have already watched the videos, or you are supposed to watch the videos, you will get to know all the derivation, equations, and how the process is established, all the things. So that's why I just wanted to discuss about the important findings from all the three lectures, because today I haven't discussed all the topics one by one, which is been said in the lecture, because those three lectures were really very long. I cannot describe them. So that's why this were the process parameter. Now let's move on to the question answer that I am having. Let's discuss about these questions, and if time permits, then we can again come back to the lecture videos and include some more topics. Or yeah, talk about something more about WAM. Okay, so this is our first sum. If you are having the lecture note, you'll have the formula. If you're not having the lecture note, if you have watched the videos, you may know. So the question is, a thin, these are previous year assignment. These are solved assignments. I'll solve it. You will get similar questions in your this year assignment. So this will be easier for you to attend. So a thin wall has to be built by MIG-based WAM process. First, a single bead experiment was performed on the flat surface, and a circular profile of the bead cross section was obtained. Find out the height of the thin wall after deposition of the 20 layer of the same process parameter. So if we are having one bead of this height and width, we can estimate how will be my subsequent layers. So my height, this, okay. So for height, we have this equation. So this is height of one bead. This is the height of one bead, which is 2 plus n is 20 minus 1 into. Now there is the very important equation from the lecture. So I think Pranav or Kiran has watched the videos. Any one of you has watched the videos. So can you tell me the equation? Because you guys are not talking about anything in between. What was the relationship of the beads which are depositing onto one by one?
Is it finer?
Uh, can you repeat your question?
Yes, ma'am.
Can you repeat your question? What did you say?
Is
Okay.
it finer?
Minor? No, 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 no. I'm not talking about the second question. I'm talking about the first question. So in the first question, the formula is something like this, and out of it, you have to first obtain the theta one. Okay. So the theta one will be like sine inverse 4hw by h, 4h square plus w square. Now this is the h and this is the w. And now when you will obtain the theta, it will come as 1.7 this. So you will place this value here and you'll get the h answer, which is 32 point this value. Okay. So the next question: consider a block deposited by MIG wire arc additive manufacturing process. In this block, the microstructure are usually thinner, close to the newly deposited layer as compared to the previously deposited layer. Now, can you tell me the reason behind this thin microstructure close to the newly deposited layer? What is the reason behind it? As I think Pranav has already said thinner. So why is it so? What should be the probable cause according to you, as you have said thinner? So, as the question says, consider a block. This is the block deposited by MIG process. In this block, the microstructure are usually finer, close to the newly deposited layer as compared to the previously deposited layer. So now think about the last layer. This is the last layer in which you are having the finer microstructure than the previously deposited layer. Because when each time you deposit one layer, you purposefully remelt the previously deposited layer. Now, the most beautiful and important criteria of additive manufacturing is it is a very fast process than casting. The deposition rate is very high than any other conventional manufacturing process. Deposition rate is very high means the arc in case of MIG process, the arc along with the consumable electrode is moving very fast over the build plate. As it is moving very fast, so the heating rate and cooling rate in case of this type of processes are very high. As the cooling rate is very high, so your layer is getting cooled down very fast. Now your layer was completely melted because you are depositing melted material, melted metal. So your melted metal, which is in liquid state, which is something having the temperature something around 1000 degree centigrade, is getting solidified very fast. Means from 1000 degree, it is coming to near to 100 degree centigrade very fast. As the cooling rate is very high, there is the chance for the microstructure to be very fine. Now, if the microstructure is fine, it is good. Because of the high cooling rate, we get fine microstructure. Well and good. Then why we are talking about like the microstructure near the first layer, near the last layer is finer, and in the previously deposited layer it is coarser. Why? Because not even coarser, they are mostly columnar. Because now you imagine when you are printing, you have printed this first layer, you have solidified, so finer microstructure. Now you are printing the second layer onto it. When you are printing the second layer, this will be finer because this will solidify very fast. But at the time of melting of this layer, this current layer, your previously deposited layer will also get heated up and melted. And as you have now deposited the second layer onto first layer, the heat will be dissipated from the second layer very high, very fast. But the heat which is containing in the first layer now, which is contained in the first layer now, will not get dissipated very high in a very high speed. The heat is high, but dissipation is low. So now there is heat contained in the first layer. Now you are again depositing third layer. At the time of third layer, again second layer is remelted. First layer will also get some heat. So this is how when you deposit thousand of layers, two, three previously deposited layers get heated up every time. And at that time, they do not get sufficient space to dissipate the heat. So they dissipate the heat slower than the current layer. So that is why when you are printing the last layer onto the last layer, there is no upcoming layer. So that's why last layer will solidify very fast. This is air. In air, it will solidify very fast. But what about the previously deposited layer? They are not having that air. They are having layers in the above and in the below. So that's why their heat dissipation is slower. So as the building direction in this plus Z, they produce columnar grains like this. And if you see the last layer have this finer grades. So that is why the answer is finer. And this is applicable to any metal additive manufacturing process, whether it's LPBF or whether it's E-beam PBF or whether it's laser DD, wire DD, powder DD, EBOM, anything. The next question is, which of the following is most suitable metal transfer method in MIG? So it's pulse metal transfer, means if you are using the AC. Then in MIG welding process, the straight polarity gives dash bead penetration, while reverse polarity gives dash bead penetration. What should be the answer? Try something.
Ma'am, large is small.
Yes. So in case of straight polarity, means where you make the electrode negative, you'll have large penetration. What is there? What is useful in case of TIG welding? But for MIG welding, we use the reverse polarity where you'll get smaller penetration. Next is in the CMT MIG welding process, a dash motion of the wire assists the droplet detachment during the short circuit. Try to answer.
Rotating motion, ma'am.
It's retracting. In case of CMT, it will get the retract back as soon as it creates the short circuit. Cold metal transfer CMT MIG welding is one of the most preferable MIG welding process due to which characteristics?
Low heat input, ma'am.
Yes, it is low heat input. Then in a MIG welding based wire or additive manufacturing process. So this is a sum again. Let's try to find out the formulas. So torch speed, torch means the consumable electrode, okay? Torch speed is 500, okay? Mm, where is it? Okay, bead height is 3 mm. Penetration depth, wire diameter, wire welding current, feed rate, material density. What will be the deposition rate? Now, to determine the deposition rate, you may have two ways by calculating from torch side, by calculating from the width of the deposition that you are having. So, the other way is where is it every time? So, the other way is deposition rate equal to AW VW into rho. AW means pi by 4, 1 is to 10 to the power minus 3 square into V is this thing. So this will come something around 16 pi. Okay. Then our next question is, in a single bead experiment using MIG-WAM, the bead cross-section profile above the substrate is found to be symmetric parabola. If the bead width is 3 mm, what will be the optimal value of step over? Step over means that overlap. So as I said, that overlap ratio has a equation like this. So 2 by 3 into 3, so it will be 2. Okay. Any question? Any doubt? You understood?
No, ma'am.
Okay. Next is, for the process explained in question 8, this thing, this 8, what will be the value of optimal step over? So again, step over S equal to 2 by 3 width. So 2 by 3 2 pi is equal to 4 by 3 pi. So why I have written 2 pi, you will see now. Because for the process question number 8, because I have solved this thing, so I know the answer. Here you have to calculate the width. So now width का formula आता है हमारा 3 pi 8000, because 8000 was this feet. 1 by 8 into 3 row into 3 into 500. So which is coming as 2 pi. So the question was to determine the width from this. So you have these things. Where is it? Okay. This is the formula. Okay. from which we have determined the answer to be 2 pi. And from 2 pi, you can put the value here and get the uh, 8 pi by 6. So again, another sum. So this sum is really big. So I will rather write down the formula. So for the process explained in question 8, what will be the approximate value of the minimum required power in watt? The formula I'm going to write here. This formula is useful for any heat input wala AM process, like wherever there is heat input like laser or electron beam or arc or plasma, you will use the same formula. Okay, uh, for LPBF, or like for powder bed fusion or for direct energy deposition, the same formula will be used, because this is the fundamental equation of the power from energy source. Cp delta T plus latent heat of fusion of the substrate and of the powder or wire or electrode, whatever the process is, dependent upon that, you just note down. Eta is the efficiency. It will be efficiency in case of arc. It will be absorptivity in case of laser. Okay. So the question answer will be 10,075. That's why a range has been given. So if we are writing this answer, it will be correct. The next question is, if the residual stress in the part produced by MIG WAM process is more than the UTS of the material, then dash will occur. If the residual stress is lesser than UTS, more than UTS, then the material will have something. What should be the answer?
I'm undercut or cold slut, cold shut.
No, it's always remember this undercut, cold shut, these are uh, like what should I say? These are useful for welding process, but here apart from welding, we are doing additive manufacturing. So one thing is like residual stress. In case of welding, the residual stress is, yeah, it is affecting parameter. It is an influential parameter, but it's not that much what it has in case of additive manufacturing, because additive is layer by layer. In welding, you'll have even if you are having any residual stress, it will be a very lesser type of compressive residual stress or something. But in case of additive, you can have tensile compressive both, and with layer by layer you will have an increased amount of residual stress. So that's why this undercut, cold shut are defects seen in welding, but the most defect in additive is the crack. So if your residual stress is more than ultimate tensile strength, then that means you are having some more stress developed inside you, which can never be overcome by your Hooke's law or by your dislocation movement inside the material or by strengthening it. No, you will not get rid of that residue, that excess amount of stress which is present inside. What will happen? It will generate the crack inside your body. And if your residual stress is lesser than UTS, but it's more than your yield strength, then your residual stress will have some effect, but it will not be able to produce the crack,
Ma'am,
but it will produce something. Yes. Yes, yes.
Screen is not visible, ma'am.
Okay. I am not writing anything, so don't worry.
Okay, ma'am.
Uh, okay. So if as much as your UTS, then it will try to deattach the layers from each other. So deattach the layers means it will have the warping from the build plate. So if this is your build plate, your part will be like this. This is warping. And crack तो पता ही है. So this is very important question. This question is really very much meaningful and important. You should always remember this type of funda in metal additive manufacturing. The next is in MIG-WAM process, a layer is deposited on substrate which was not cleaned properly. What type of defect likely to occur due to this reason?
Porosity, ma'am.
Mm, I am not sure about this answer because um, warpage, porosity, every type of defect may occur, but how this question was set, I don't know that which preference, what was the preference given to the answer. So I'll not much comment on this. Let's move on to the next question. In MIG process, the raw material induced porosities are due to dash, process induced porosities are due to dash.
Ma'am, surface contamination, unstable process.
No. Raw material induced porosity and process induced porosity. So रॉ मटेरियल से आ सकता है तो वो तो सरफेस कंटामिनेशन हो सकता है और प्रोसेस से आ सकता है तो वो अनस्टेबल हो सकता है तो ये उल्टा होना चाहिए ये सरफेस मतलब यू शुड बी राइट बट माय आंसर इज नॉट matching with yours. Maybe you can check with your quiz, but this was the given answer in last year. Okay. In TIG WAM
Okay.
process, rotating wire feeder is often used to achieve it is omnidirectional because when you are using TIG, the arc is coming like this and the wire is coming like this. Now both the things are attached to the head. And when you move the head, sometimes when you are depositing here, this is the top view. When you are depositing here, the wire is coming in the front position to the arc. When you are printing here, the wire is coming in the back to the arc. When you are printing here, the wire is coming to the side to the arc. So there are very disturbance in the process. So that is why it is called omnidirectional. So rotating wire feeder is used. In MIG WAM process, generally
Ma'am,
ideal.
omnidirection means
Yes, yes.
omnidirection means single direction, ma'am.
Get the omnidirectional to get a single type, like if the arc is like this and your wire feeder is like this is coming in front, this is front. Okay, so this is one configuration. Now you want to maintain this configuration because if you are melting the wire like this, you will get certain bead height, width and the property. If you are melting the wire like now the arc is coming in the front and wire is behind, you will get different bead height, width and property, and you don't want it. So that's why you need the omnidirectional, one direction feed. But using constant wire feeder, you cannot get that. So that's why we use rotating wire feeder.
Okay, ma'am.
So the next question is, in MIG process, usually the adjacent layers got delaminated due to incomplete melting of the substrate. In TIG WAM, the wire feed process is dash. What should be the answer?
Dependent on standoff distance.
It should be dependent on standoff distance. It should be dependent on voltage. It should be, but the wire feeding rate is also dependent upon the deposition process, but it should not be controlled depending upon this process parameter. So it will be controlled separately, but it is like having the influence along with the other parameters. Okay, wire feeding process is separately controlled, but it will have the influence along with the other process parameter. So it is dependent upon the other current voltage, not current voltage, but standoff distance and the deposition rate, but it will not be controlled like this. So our next question is, which of the following wire feeding mechanism is preferred? So it's front feeding. In front feeding only, what I showed there, from the front the wire is coming, then the arc, this is the arc, and you have to maintain it, so rotating disc will serve the purpose. In WAM, an inert gas is used for ionization and establishment of the arc. So plasma where WAM may we use inert gas for the ionization and establishment of the plasma or the arc. This is the last question. I max के साथ R का क्या relation होता है? This is same as what we have seen in FDM actually.
But the curve is similar to when we see FDM.
Yes, it's similar to FDM. FDM में भी तो वही वही है ना, सेम ही है. But here we are producing the electricity and using electricity. There we do not use the electricity. We just try to maintain the tension, compression, and the buckling to avoid the buckling, all those things. Okay. So this is all about this week 8 lectures and the previous year questions. I hope you have understood. If you have any doubt in any topic, you can write down the doubts. You can send me via mail, and there is, I think, one feedback form uh, circulated among you, so you can fill that feedback form. You can write my name also, whatever you feel, whatever I should see or something. I cannot see that feedback form, unfortunately. I'll get that after the whole series of week 12 are completed. Anyway, that will help me in my TSA, which I'm doing here. Okay, so if you do not have any doubt, then we can stop here.
Ma'am, you will discuss about last week's assignment, ma'am.
Okay, that I completely forgot. I'm so sorry. I forgot to see that question in. Yeah, you asked me something about the SLA process, right?
Yes, ma'am.
Okay, okay. I forgot to see the question from the assignment. Can you tell me the assignment number, like which week assignment it was? Then I can see it.
Which one? S11, ma'am.
Yes, SLA one.
Week 2, ma'am.
Week two. Okay,
Yes,
I'll
ma'am.
surely see this thing and get back to you. Okay, I'll see if the question is there and what is the thing. Okay. Other than that, anything else?
Previous week,
Anything?
ma'am.
Which thing? Sorry, can you repeat?
Ma'am, previous week assignment, ma'am. One question is there, ma'am. 18 question.
Previous week 18 question.
Yeah,
Means
ma'am.
week 7 18. Week
Not
18
previous.
question. And what is your doubt?
In this year's assignment.
Yeah, yeah. What is your doubt?
How it is? Can I start reading the question, ma'am?
Yes, yes.
If the minimum possible area of the deposited bead in FDM is equivalent to the area of a 2 mm diameter circle, then the standoff distance is given by 2 pi
This is the
millimeter
okay. Hmm.
pi millimeter, pi by 2 millimeter, and none of the above.
Uh, area of 2 millimeter radius circle or diameter?
Diameter, ma'am.
Diameter. Okay. And the options are 2 pi, pi by 2.
Yeah, ma'am.
Okay. So what was the answer and what is your doubt? Did you not find out the formula or you have the doubt in your answer? I,
Doubt in my answer, ma'am.
I don't remember the in the answer. What was your formula used and what is the answer came? I cannot find the equation. Maybe. So, do you know the formula? Can you tell me?
Wait, ma'am. I will see my notes, ma'am.
Okay.
The formula is AB minimum is equal to h square by pi.
Yeah, AB minimum equal to h square by pi. Yes. So the h is the stand-off distance. So AB minimum into pi root over. This should be the answer then.
H is equal to pi will come.
So it's pi. Yes, the answer should be pi. What is the answer came in your case, and what is the written answer there?
2 pi millimeter, ma'am.
Ah, it should be pi. If you like this thing, I really think this should be pi. So you may ask you may raise this doubt to the directly. You can mail them. If they feel that this is the right answer, they will correct the answer in your assignment. And if they feel no, there is some other equation, they will solve there. Because according to me, this should be the pi should be the answer. If 2 millimeter is the diameter.
Okay, ma'am.
Okay. Anything else?
No, ma'am.
Okay. Okay, then we can stop here. Thank you for attending. Bye bye. Good night.
Thank you, ma'am.